Okay, so thank you so much, Professor Alejandro, and thank you to all of you for attending this meeting. So, okay, I will start by I don't know, this is not working. It's not working. No? Okay, thank you. So, okay, today I will be talking briefly about an introduction of some of the concepts I will be talking about along the presentation. Then I will present to you some of the basics of delta F particle in cell method, okay, with some examples also. Then I will present to you some of my ongoing research, which is about turbulent transport in Hall thrusters, okay? And so okay, first, I think it is important to place some of the topics I will be talking about in this big picture of what computational plasma physics is. So for example, in computational plasma physics, basically we can do three things. For example, we can do a simulation. This can be, for example, kinetic, with a kinetic description, or maybe with fluid description. For example, in kinetic description, we usually want to simulate a problem based on Blasov or Fokker-Planck equation. Or maybe we use particles to sample some distribution function, which is the basics of particle in cell. Or maybe we can use this other scheme, which is called delta F particle in cell. That is the main topic of this talk. Or maybe we are interested in fluid description, where we usually want to simulate a problem based on MHD or two-fluid description, okay? But we also could do a numerical solution, and this is very important because numerical solution differs from a simulation, because in this case, we usually have an analytical model, and we want to evaluate it with raw data from an experiment, for example, okay? So, for example, we can solve a dispersion relationship, we can solve an eigenequation, or maybe we can solve ODEs, PDEs, etc. Or maybe we are interested in data processing, which is also very important. And, for example, here we can do data analysis, for example, spectrum analysis, smooth interpolation, fitting of some of that raw data. Or maybe we are interested in data visualization, for example, producing images in 1, 2, 3D, or animations, movies, etc. Okay? So as you can see here in this talk, I will be talking about basically about the delta F particle in cell, which is a simulation method, and also about the numerical solution of an analytical model, which is a dispersion relationship. Okay, so first of all, what produces plasma in classical plasmas? Okay, turbulence in classical plasmas. So in plasmas, gradients, typically in density, in magnetic field, or maybe in temperature in one of the species, typically provoke instabilities. Then through saturation, which is a nonlinear effect, the amplitude of these instabilities grow. And when these higher amplitude waves interact with each other non-linearly, the plasma configuration rearranges, becoming chaotic, and consequently producing turbulent scenarios. For example, this is a simulation of plasma microturbulence, and as you can see, is a range that is very chaotic, right? So as we saw, the first ingredient, very important to study turbulence, is which is called an instability. But the main question will arise, and well, how can we study these instabilities, right? So this typically is through an analytical description, which is, for example, a dispersion relationship. And when we solve this equation, we obtain solutions like this. For example, these are complex solutions where the real part of the solution represents the frequency of the wave, And the imaginary part could be one of these three cases here. For example, in first case, if this imaginary part is negative, we said that we have, for example, a damped wave. And from a turbulence standpoint, this is not an important solution. Or maybe this imaginary part could be zero. In that case, for example, we have an unstable wave. And also from a turbulence standpoint for a turbulence study, this isn't an important solution either, okay? But what happens when the imaginary part is positive? Well, this is what we call an instability. Or for example, the wave has unstable behavior. And therefore, for turbulence study, this is the key solution that we are looking for, okay? So please keep this in mind because it's basically the rest of the talk. I will be talking about something around this, okay? So let's jump to delta F particle nacelle method, okay? So first of all, let's talk briefly about what is particle nacelle. I think some of you are very familiar with the method, but I think it's necessary also to do some brief reminder. For example, particle nacelle is a kinetic simulation, like we saw at the beginning, that uses computational particles to represent the dynamics of charged particles under the action of electromagnetic fields. That is the basic idea of what we do with particle nacelle, right? Then we can summarize the main cycle of this method like this. For example, once we load the computational particles into the domain, which is typically a mesh, a computational mesh, we can calculate the charge and current densities and interpolate these values to each node in the domain, okay? Then with this information saved in the nodes, we can compute electric and magnetic fields here in the nodes. Then this information is interpolated back from the nodes to the particles, okay? And because these fields can produce that the particles move in the domain, and for example, with these new positions and velocities, we can repeat all this cycle over and over again for a number of time steps, okay? So that's basically what we do with particle nacelle. So let's say we want to simulate a specific problem. Here I put, for example, a weak beam plasma instability, okay? But this instability is very common in plasma physics. And for example, it arises when a big beam of particles is injected into the plasma. For example, let's think, for example, a weak beam of electrons into solar wind plasma, for example, right? So originally we have, for example, let's imagine this distribution function for the electrons in the plasma, right? Before the injection of this weak beam. Then, because this weak beam of electrons enter into the plasma, we will have something like this little bump on tail. In fact, this type of instability sometimes is called like bump on tail instability, because these new electrons will combine with the electrons we have here on the tail with high velocities, and then the distribution function will have this little bump here, okay? In other words, we have more electrons in this region, okay? So basically, the instability arises because the change in the slope of the distribution function in velocity space here in this region, basically. So what we do with particle nacelle is try to sample this problem, this distribution function with particles, okay? So in order to simulate what happens with this problem. So,
sorry, could you please come back?
Okay.
So you always have to choose higher velocity particles, no? In order to have this bump.
Yeah.
With respect to the original distribution, right?
Yeah. For example, this weak beam is weak in nature. It has a very low density, but the electrons are very energetic, so the velocities are very high. So that's why they combine with the original electrons in the plasma in this tail, and That's why this bump is formed in this region, okay? So if we want to simulate this problem with particle in cell, we will obtain results like this. For example, here we have in this figure two cases. For example, here we have this normalized beam density, which is around this value. And you can see that here we can briefly see the linear growth rate of the instability, right? But the thing is that for the rest of the time steps, we have all this statistical noise, and it's not very clear what we are seeing here, right? In a way, the physics that we want to see is obscured by all this statistical noise in the results. But for example, what happens if we want to simulate this same instability, but employing a much weaker plasma beam, okay, with this normalized density? Well, here, obviously, we can't see any linear growth, and is all this simulation is taken over by statistical noise, and we can see pretty much anything, right? So even though we use here more particles, we went from, for example, in this first case, a million of particles, and in this other case, 10 million of particles, we can't see anything. So in a way, we can draw this, okay.
So in this case, both beams have the same speed distribution? Or?
Yeah. Yeah, the only thing that changes is the relative density of the particles. In other way, for example, here, we employ much more particles in this beam, and in this case, much less particles. Okay. So some of the conclusions that we can draw from this simulation is that, generally speaking, particle in cell becomes a noise problem, okay? For example, if we want to scale up the resolution of the results, we usually include more particles into the simulation. But at the same time, the drawback is that the noise also becomes higher. So it's not pretty good, right? Therefore, for specific problems with weak turbulence, for example, when the magnitude of the growth rate of the imaginary part of the solution is smaller than the frequency of the wave, well, in these cases, we can use the delta F particle in cell because there is more convenient, like we will see in a minute, okay? So for example, what are the main ideas of delta F particle in cell? Well, the general idea of this form of peak simulation scheme is to exploit the advantage that in many problems of interest, the physical fluctuation of the kinetic distribution function is often much smaller than the total distribution function, okay? Therefore, separating the total distribution function into an equilibrium part and a small perturbation, we can solve the equilibrium analytically, for example, choosing a Maxwellian well-behaved and well-known distribution, and use the computational particles of the peak method to simulate the fluctuation part only. For example, let's say we want to simulate the same problem, okay? So usually with particle in cell, we will use all the particles for sampling all these distribution function. But here comes delta F simulation and told us, well, what if you could represent this problem as the sum of a Maxwellian distribution function, okay? This Maxwellian distribution function, and a small perturbation. So you can solve the equilibrium part, the well-behaved part, the well-known part as the Maxwellian form, analytically, and only use the particles in the peak method only to simulate this little perturbation. Okay, so that's the main idea of this scheme, right? So if we do that, well, these are the equations, the general equations that we are using for the delta F particle in cell. As you can see, we have the classic two equations of the particle in cell. for example, the evolution of positions and velocities, but also in this new scheme, we have these other equations that are the evolution of these other two parameters, right? The W and P. And W is related to the perturbation, okay, in the distribution function, and P is related to the equilibrium part of the distribution function. Okay, so normally we use these equations to perform a delta F particle in cell simulation. And as you can see, also a very important advantage of this scheme is that we can directly perform linear simulations if we write these equations in a linear form, right? Okay, so let's go back to the problem of the weak beam instability. And for example, if we use this delta F particle in cell, we obtain these results. And as you can see, it's a huge difference, right? Between this and the total F particle in cell, because here, as you can see, very clearly, very smooth, we can see the linear growth rate of the instability, okay? And also, we use less particles. So from a computational standpoint, is something very convenient. Also because the computational resources and all of that is something that we can also use by this new scheme, right? Okay, so here we can compare back to back the results of the delta F particle in cell with the total F particle in cell. And as you can see, it's a huge difference. Now, some of you maybe with a keen eye will notice that, for example, in this case, the delta F particle in cell, we performed this simulation for around 1,000 time steps, okay? Instead of the 600 or more or less time steps in the total F particle in cell. And maybe you are wondering why. Well, the reason is that, for example, in this simulation with the delta F particle in cell, this is a nonlinear simulation. And we can see, because, for example, here we have this very clearly this growth rate of the instability. But what happens in this region? Okay, so here, this is the result of the nonlinear saturation that eventually will lead us to turbulence. Okay, so for example, we have this linear instability, and then this instability is saturated by some nonlinear mechanisms, and then we can see here the result of that nonlinear taking over. Okay.
So is the beam ejected throughout the whole time range, or just at the beginning?
Yeah, from the whole time. Yeah, it's continuous.
And in the second case, in the B panel,
yeah,
it's the same.
It's the same. Yeah, the only difference is that, for example, here we only conduct the simulation, the total F particle in cell, for around 600 time steps. Okay, but in this case, we need to extend these time steps to see the nonlinear saturation. Okay, if we, for example, ended here, we can clearly see the linear growth rate, but we haven't seen yet how the instability is saturated by the nonlinear effects, right?
If we were extend also, we can expect in the second case, you see what's all this noise.
All these noise and even worse maybe. Okay. Okay. So now let's present some of the results that I obtained from my ongoing research, which is turbulent transport in Hall thrusters. And first of all, let's talk about what is a Hall thruster, right? So a Hall thruster is a specific type of device that belongs to the family of electric propulsion, okay? Also called plasma propulsion for space vehicles. And here are some of the main features of this thruster. For example, the plasma is generated in this annular discharge chamber, okay? But here we have a particular E cross B field configuration, okay, which is very particular of this type of thruster. For example, this type of thrusters has a high level of technological maturity, produces high specific impulse, low thrust. As you can see, the thrust that this thruster produces is very, very little. That's why this is only used in space, because we have vacuum in space and we don't need very large quantities of thrust. And for example, it's used on board of communication satellites, for example, Starlink, for correction or an in-orbit positioning, but also it can be used for on board of deep space exploration probes, because these type of thrusters can operate for months and months and even years and years, okay? So, for example, in this cross-sectional diagram, we can identify some of the main components of this thruster. For example, we have here the chamber, this annular chamber, okay? At the base of it, we have this anode, excuse me, this anode and some ducts that help us to inject the propellant inside of the chamber, okay? Normally, we use as a propellant, we use noble gases such as xenon or krypton, because they are very easy to ionize, okay? So here at the exit plane of the thruster, we have these magnets that impose a radial magnetic field in this region. And finally, we have this sort of tubular section here that is a hollow cathode that emits electrons. So these electrons are attracted electrostatically by the anode at the base of the chamber. So when they enter into the chamber, they found these magnetic field lines and they become confined in this region. Then we inject the propellant, and these neutral atoms collide against the very energetic electrons and they become ionized. So an electric field, this electric field accelerates these created ions inside the discharge chamber and forms the beam of propulsion, the plume, okay? So finally, a fraction of electrons from the hollow cathode help us to neutralize the space charge in the plume region to prevent the charged particles could flow back and impregnate some of the spacecraft surfaces and a lot of that, okay? So as you can see, some of the basics of the operation of this type of thrusters could be more or less easily understood. Nevertheless, because we have this field configuration, which is very particular, we have the existence of gradients in plasma density and electron temperature, magnetic field, and several instabilities appear in the plasma discharge, provoking the development of turbulent scenarios leading to which is called the turbulent or anomalous transport of electrons from their confinement zone to the anode region and at the base of the discharge chamber, okay? So this anomalous transport causes a series of operational problems, among them an increment of electron current needed to maintain the discharge that doesn't translate into effective thrust, okay? Decreasing the overall efficiency of the thruster and affecting the lifetime of the thruster and the mission itself. So we don't want that that anomalous transport to happen. So one of the main drawbacks of this technology is that still there is no consensus to describe the relation between these several instabilities and their relation to turbulence formation. So the design of these thrusters remains semi-empirical with long and expensive experiments waiting for a full computational IVET designed to assess the anomalous transport successfully. So that's basically what my research is all about, to study this relation between instabilities in the plasma and how that instabilities led us to turbulence and anomalous transport and all of that problems. Okay? Okay. So, okay. So the question is how we can theoretically tackle anomalous transport. So in classical magnetized plasma physics, it was proposed decades ago that turbulence from microscopical scales. This is very important because this, as we will saw in a minute, is the basic foundation of what type of theoretical framework we are working with, okay? So turbulence forms from microscopical scales, and it could be closely related to drift waves, which is a very specific type of waves and instabilities associated with gradients. Okay, so when we are interested in low frequency waves at scales comparable to gyro radius of particles, in other words, we are in microscopical scales, we can average the fast cyclotron motion of particles around the magnetic field lines. And this new theory was called gyrokinetics, okay? And has been the most successful analytical tool to study turbulence and anomalous transport in the last 3 or 4 decades. Okay? Mainly for the communities in fusion plasmas and magnetic confinement plasmas and all of that. So if I'm interested in studying turbulence in this type of thrusters, first I want to have an analytical equation that gives me information about instabilities in the plasma configuration. And that's why I derived this model, this dispersion relationship, using gyrokinetic electrons and fully kinetic ions. Now, maybe you are wondering why I use this dichotomy right here. And the answer is that, for example, gyrokinetics is only applied to magnetically confined plasmas. So the only species in the plasma that is confined magnetically, in this case, are the electrons, while the ions are basically, they are formed and they are accelerated towards the exit plane of the thruster, and that's it. Okay, so that's why here, for the ions, I have a fully kinetic description, and for the electrons, I have this gyrokinetic description. Okay, so now, from this analytical equation, this dispersion relationship, I solve it numerically and using, for example, data of this specific type of thruster, Hall thruster, the SPT 100, and I obtain these stability results. So as you can see, pretty much for the vast majority of actual positions, we have either a stable wave or a damped wave. But also we identify some intervals of positions where I have this unstable behavior. Okay, so at this stage of my research, I'm only interested in localized modes. So what I do is from this interval, I pick only one specific point, okay? And then I analyzed what is the stability behavior of this particular position inside the discharge chamber. And these are the results, okay? As I told you, with the dispersion relationship, we obtain a complex solution where the real part is the frequency of the mode, and the imaginary part is in this case, for example, because we are talking about an instability, is the growth rate. Okay, so these results are for a number of wave vectors. Okay, so as you can see, for example, from here to the value of 2, we have unstable behavior. But from this point onward, we have this instability is damped altogether. Okay. So the next step is use delta F particle nacelle to simulate this same problem for this specific position inside the discharge chamber, and pick one of these wave vectors that give me an unstable behavior. Okay? So these are the equations that will be that I solve for the delta F particle in cell simulation of this problem. And as you can see, this is the equation for electrons, and this is the equation for ions. And these, for example, are the specific delta F particle in cell model equations that I will solve in the simulation. And for example, note that in this group of equations, the only unknown is basically this perturbed electric field. Okay? All the rest, I solve it analytically inside the method. Okay? So in other words, I only use the particle in cell particles to solve this electric field, this perturbed electric field. Okay? And when I do that, I obtain these results. For example, here we have this perturbation in electric field, okay? The real part and the imaginary part. Here in this other figure, we have in logarithmic scale this same perturbation in electric field. And as you can see, thanks to the delta F particle in cell, I can see clearly the linear growth rate of the instability. But what happens if I measure the slope of this linear growth rate and also the period of this signal? Well, then I obtain the frequency and the growth rate of this instability. So I can compare these results given by the delta F particle in cell simulation with the results given by the analytical dispersion relationship. And as you can see, maybe, I don't know, but maybe you can see that they are very close, okay? So this gives us a very good amount of certainty that first of all, that the analytical equations that we propose to simulate, to describe this problem are very well corresponds very well with the delta F particle in cell simulation. Okay, and finally here I plot the transport coefficient, okay, which is related to the flux of particles as a product of this instability. So look, these are linear results, okay? As you can see here, I don't have the saturation mechanism. Yet, for example, as you can see, I highlighted here in blue this nonlinear term that is responsible for the nonlinear saturation of the instability. So in linear simulation, I put this equal to 0, okay? So these are the linear results, and then I turn on the nonlinear term, and I obtain these results, these nonlinear results, okay? So as you can see, there is a clear increase in the amplitude of the instability, right? We have here the nonlinear saturation mechanism that takes over the instability and starts basically at this stage. We can see this increment in the amplitude. We compare here the linear part, the linear growth rate with the analytical results, which are very good. And finally, we have here something really interesting, because as you can notice, here in this region where we have this nonlinear saturation, we have an increment also in the transport coefficient, in the anomalous transport or turbulence transport. So with these results, we can have these partial conclusions. For example, first of all, we see how delta F particle in cell simulation permit us to obtain practically the same results of the linear growth rate as the analytical one-dimensional electrostatic gyrokinetic dispersion relationship. Also, when we perform a nonlinear simulation, we can observe the saturation region and a clear relation to the augmented turbulent transport coefficient, confirming what theory says about the close relationship between instability, nonlinear effects, turbulence, anomalous transport. Okay? Nevertheless, at this stage, we need to include more physics into the model. For example, the influence of electric field over the ion species, the magnetic field gradient, and the effect of Larmor radius over the electron species, right? Also, we want to obtain a higher dimensional model. For example, we are talking about maybe it would be great to have a two-dimensional model, especially to assess the impact of the configuration space nonlinear saturation mechanism, which is other saturation mechanism, and among other phenomena, right? So, well, that's basically what is at this stage on my research. And finally, I put together this sort of list where, for example, I recommend you to check some references according to your specific interest. So maybe if you are interested in theory, you can check some of them, and or if you are interested in numerics, well, I put these references. Okay, and well, that's all. So thank you. Yeah.
Okay. So I have a couple of questions. One of them is short. Did you perform the experiments that you were?
No. No, that's a very good question, because, for example, to perform all these simulations and the numerical solution,
yeah, the one with the,
for this specific type of thruster, this information is very scarce in the literature. This, for example, I obtained it from a study that reported all the measurements of the various variables in this type of thruster, and I used that information to construct a database to evaluate all these models. So no, I don't perform it.
Just a comment in that case,
yeah.
Maybe it would be nice to give the reference. Otherwise, I thought it was part
yeah.
of
yeah. Yeah, you're right.
And then, so you're saying you work with delta F.
Yeah.
So this means for these thrusters, as you mentioned, you work with very low densities as your outer space, right?
Well, the low densities were only to the specific problem of weak beam stability that I used to kind of illustrate the advantage of delta F particle in cell. But in this case of the whole thruster, we have the densities that are usual in these type of thrusters, and they are very large.
Oh, I see.
Okay. Yeah.
Okay. So you're working with the densities just outside the thruster.
Inside the discharge chamber, for example. Let me go back. Here, for example, in this simulation, I runs the evaluation of the dispersion relationship using, for example, data from this very region at the base of the discharge chamber, going through all this discharge chamber up to the exit plane, and also we have information about a little region in the plume. So I performed the simulation for all this domain.
All right.
Right.
More questions?
I'm a little bit confused. In these simulations, you are in the non-relativistic region?
Yeah.
Yes.
Yeah.
Okay. And this perturbation you introduced is also in the non-relativistic region?
Yeah. Yeah. In fact, all this talk was about classical plasmas. I know that, for example, some of you, if not all of you, are very interested in relativistic plasmas, right? And for example, I know that some of these specific quantities may you should calculate it in your specific case. For example, when I talk about the Larmor radius, I know there are a type of a calculation that you need to do for assess all the non-relativistic problems, and for example, the velocities and all of that. But I have to be honest, and I don't know if, for example, in the model, in this model, I assume that you need to modify these equations according to your specific problem, right? Because at the end of the day, these equations are derived from the Blasov equation, which is a classical equation that describes the dynamics of plasmas in electromagnetic fields and all of that. So maybe in relativistic plasmas, you need to start from another equation and construct something similar. Okay.
From my understanding, the goal is to contribute towards the development of more efficient ball clusters. Right?
Yeah.
So, how efficient are they right now, and what would be their outlook on increasing the efficiency? Because from my knowledge, they are very efficient.
Yeah, they are efficient because, as I mentioned, they have a large history of successful flights in space, and they are used. For example, in Starlink, we have thousands of satellites that use this type of thrusters. But the thing is that, for example, we can improve the efficiency. So maybe they can stay in orbit for a longer period of time. And also, for example, if we are interested in deep space exploration, this type of technology is like very good for that. But we need to solve all that efficiency problems, right? So basically, the main thing that harms these type of thrusters is basically the production of turbulent transport based on, well, all that you see.
Question: what is roughly the outlook on increasing efficiency?
The what?
Roughly speaking, how much efficiency are we using due to turbulence? Roughly speaking.
Well, we have, for example, for this type of thruster, maybe this particular, the SPT 100, we are in efficiencies around 60%. So it's not stellar, but it's relatively good for the applications in space, but we want to increase that, right?
More questions? Well, I have one. Why not keep constantly background? Because I understood from the beginning that you are only doing evolution of delta X, but you're really also evolving the background.
Yeah, well, actually the background is described by the equilibrium part, and that equilibrium part is constant.
Okay, because you say that it's analytical, but then it's really constant.
Yeah, well, I said it's analytical because this distribution function has a very clear, very well documented form in literature, and so, for example, when we are interested in calculating these terms, we can use that analytical form, calculate it, and obtain something like this. Okay, all these gradients and all of that.
Okay.
Yeah. So I actually wanted to ask you what kind of shape does F0 have?
What type of shape F0 of the equilibrium part? Yes. Well, a Maxwellian form.
So it is actually Maxwellian there.
Yeah. Yeah, we are using the equilibrium part described by a Maxwellian form like this. Yeah, this form arises from the fact that we are considering a plasma that is in thermal equilibrium. For example, if we have this cage, for example, where we have all these particles and leave it there for a specific time. And then we come back, the particles will reach thermal equilibrium and we'll have this type of form.